Hello, everyone. So let me check my audio levels, and only two people in the chat. Um, well, let me know if my audio levels are bad. My audio is bad. Uh, this particular software that I'm using, every time that I start it up, it changes the levels, and I have to just readjust them, which is why I asked the question at the beginning of every live stream. Anyhow, let me start the test. It's going to be 28 questions. As I said last time, I timed it, and it you should be able to do it within an hour. But as I said, I'll give you 2 hours, and try to do it during the time of your regular class time. But I will open it up an hour earlier, and I'll leave it open even 2 hours afterwards. Okay. All right. Well, let's just start. Last time, what I did was I did a problem on Newton's laws, and this class I'm going to do a problem on Newton's universal gravitational law and Kepler's laws. Okay, that was a short section, and then we did energy, and I'll do a problem on energy. Sorry, I'll do two problems on energy. One which is like kind of like the roller coaster ride, but at the end of one of our live streams, I gave you an example problem where I fired something straight up into the air. So we're actually going to do that. I thought that was a good problem, so I thought we'll do that with some numbers in it, and we'll also do an oscillator problem. Okay, so let's begin. This is a problem on Newton's universal gravitational law. What is the gravitational force between two 1 gram masses that are 1 centimeter apart? Okay, so between any two objects in the universe, there's an attractive force, gravity. But if the objects are small, the gravitational force is very small. That's why, like, you don't feel that you're being pulled towards the walls, or like, when you're beside your car, you don't feel like you're being pulled towards your car or something like that. You do feel that you're being pulled towards the Earth because the Earth is very, very, very big. Things that are small, they have a gravitational force, but it's very small. So that's the point of part A. And then in part B, we'll do the same, but this time we'll do it between the Earth and the Sun, and we'll see that we get a very different answer. Okay, so the formula you need for that is, let me cut and paste out of from here. It's this right here. Okay, so the gravitational force between any two objects is equal to G, capital G. That's the universal gravitational constant, and there it is right there. I wouldn't expect you to memorize that number. I would give it to you on a test, but it is an open book test. You could just Google for it. You just Google for like universal gravitational constant, and that pops up. But like I said, I'd give it to you. So force of gravity between any two objects is equal to capital G, m1, mass 1, times m2, divided by r squared, where r is the distance between the two masses, measured between their centers. Okay, and so we have uh, uh, two 1 gram masses. Okay, so it was substituting in here. For G, we have the constant there, 6.67 times 10 to the minus 11 in MKS units. For M1, we have 1 gram, but we have to convert that to kilograms, so it's 0.001 kilograms. And then the other mass is also 1 gram, so it's also 0.001 kilograms, divided by r squared, and r, I said, was 1 centimeter, and so 1 centimeter is 0.01 meters. Okay, and so there it is, and if you work that out, you get that number right there, which is 6.67 times 10 to the minus 13 newtons. Now, 10 to the minus 13 is unimaginably small. In fact, it's so small that we would not be able to measure that even experimentally. Okay, so you can imagine you have a 1 gram mass here and a 1 gram mass here, like something like maybe a ball bearing, and they're 1 centimeter apart, and you ask, what's the force of gravity between those two? And it's incredibly small. It's like 10 to the minus 12 is 1 trillionth, and 10 to the minus 13 would be a tenth of 1 trillionth of a newton, and the newton's already small, so this is so small it would not be measurable. Okay, and that's what you expect with objects that are about this, the size of us, but yeah, human level sizes. Okay, you have to get the planetary sizes before you have an appreciable force. Okay, so that's the second question. What is the force of gravity between the Earth and the Sun? And for that, of course, you need the mass of the Earth, the mass of the Sun, and the distance between the two. Okay, and so here's that. Whoops. So again, I just Googled for these numbers. And here's the mass of the Earth. I called it ME, and 5.972 times 10 to the 24 kilograms. So it's pretty big. Of course, the mass of the Sun is even bigger. It's 1.989 times 10 to the 30 kilograms. So it looks like it's 6 orders of magnitude higher. So that's like 1,000,000 times bigger. Okay, million times the mass. And there's the distance from the Earth to the Sun. This is exactly the way it came out of Google, 148.65 million kilometers. Okay. The masses are in NKS, so leave them alone, but the distance we have to convert to meters. And so the 148.65, there is that. Okay, million, that just means 10 to the 6, okay, like that. And kilometers, kilo, the K there is 1,000, and then meters. Okay, so that's how I converted from that to that. Okay, and there it is now in meters, and now we can just plug into the formula. And so here's the universal gravitational constant. Here's m1, the Earth's mass. Here's the Sun's mass, divided by that number. I guess I could have worked it out there, but that's okay. That number squared, okay, and that turns out to be that. So 3.59 times 10 to the 22 newtons. And 10 to the 22 newtons is huge, okay? But you would expect that because the Sun is big, the Earth is big, and even though they're far apart, and the further apart things are, the less gravity there is between them. That's the 1 over r squared, okay? Even though they're far apart, still the force is appreciable, okay? And 10 to the 22 is, again, unimaginably large, okay? And that's what keeps the Earth, revolving around the Sun. If it weren't for that force, we'd just go straight off off into space, and who knows where we'd end up. Okay, so there it is. That's universal gravitational law, Newton's universal gravitational law. And I don't see any comments in the chat here, so let me continue. Okay, also with planetary motion, we did Kepler's laws. Okay, now there's three Kepler's laws. Okay, but I really can't ask you questions about the first and the second. Well, just general questions, qualitative questions, but I can't ask you to do any quantitative questions with the first and the second. Uh, Strictly speaking, I could have if I'd shown you how to do them, because you do have enough calculus to do that, but that would take us too far afield from our course. So the first law, Kepler's first law, was that planetary orbits are ellipses with the sun at one of the focal points. Okay, and they could be circular, but circles are a special kind of ellipse. In general, they're not circles. In general, they're ellipses. Okay, and only in very special cases where the ellipse merges to a circle is it actually circular. But remember, all circles are ellipses, but not all ellipses are circles. Okay, so in general, the orbits are ellipses with the sun at one of the focal points. Okay, so the second law is that if you draw a line from the sun to the planet, that line will sweep out an equal amount of area in an equal amount of time. Okay, and that's kind of a hard idea to get in your head. Qualitatively, what it means is that because the orbits are ellipses and the sun is at one of the focal points, there's a period in the orbit when the planet is closest to the sun, and there's a period in the orbit when the planet is furthest from the sun out here. Okay, if the sun's like more on the one side of the ellipse than the other, and when the planet is closest to the sun, it's moving fastest along its orbit. When it's farthest from the sun, it's moving slowest. Okay, so even the Earth's orbit is very close to being circular, but it's not. It's slightly elliptical, and this is not a seasonal thing. There is a period in the year when the sun is actually moving around the sun a little bit faster than it is at another point in its orbit. Okay, the seasons have to do with the tilt of the Earth's axis. They're not. Doesn't have to do with the elliptical nature of the Earth's orbit. Okay, so there it is. Now the sun always looks about the same size in the sky, and that's because it is very close to being a circular orbit, but it's not circular. It's measurably different than a circle. It is an ellipse. Okay, anyhow, the third law is the law that I can ask you to do questions about. And it basically says that if you form the ratio r cubed over t squared, where r is the radius or the average radius of the orbit, divided by t squared, where t is the period of the orbit, the time it takes to make one revolution around the sun, that ratio r cubed to t squared is the same for all the planets. So if I give you enough information to calculate it for one, then you should be able to calculate it for others as well. Okay, and so that's the problem that I have highlighted here. An asteroid takes 565 Earth days to orbit the sun. Okay, so I'm telling you the orbital time, the time it takes for this asteroid to make it once around the sun. You know what that is for the Earth. 365 days. Okay, 365 days for the Earth to go around the sun, and the this asteroid is 565 days. Okay, and how much bigger is that orbit than the Earth's orbit? Okay, and I want that bigger. What do I mean by how much bigger? I want that as a percentage, like it's 30% bigger, 40% bigger, or something like that. Okay, and so you might think, hey, don't you have to tell me the Earth's orbit to answer this? I've got the period of the asteroid, I've got the period of the Earth's, and I want to calculate the radius of the asteroid. In other words, like how much bigger is its orbit? But like, don't I need the radius of the Earth's orbit? No, we just want like a ratio between how much bigger the asteroid's orbit is than the Earth's orbit. And all you have to do is just set the Earth's orbit equal to 1. Okay, you don't have to work in MKS units for this. Okay, you'll see that in just a second. And actually, if you take an astronomy course, that's what they do. They set the Earth's orbit, the radius of the Earth's orbit, that is the distance from the Earth to the Sun. I mean, we had it before. You could see it right here. That 148.65 million kilometers. You just set that equal to another unit, and you call that 1 astronomical unit. Okay, and so then the radius of the asteroid's orbit will come out in astronomical units, and you'll just be able to compare 1 to the radius of the asteroid's orbit in astronomical units, and you can answer the question that way. Okay, so let me give you the solutions, and you'll see that you don't have to work in MKS units at all. Where are we here? All right, there we go. So here's the formula. All right. And if you just concentrate on this side right here, okay, the subscript E means Earth. So that's Earth's orbital radius cubed divided by Earth's orbital period squared. Okay, so R cubed over T squared. For the Earth, that's the same for the asteroid. And over here, it's the same thing, but with subscript A. Okay. And uh, for the Earth's well, sorry. Why the units not matter here? Why don't you have to convert to MKS units? Well, that's because if you're working in astronomical units for R, you'll get astronomical units cubed here, and you'll get astronomical units cubed there. And if you work in days there, you'll get days squared there and days squared on the other side. So as long as you're measuring all the distances in the same units in this equation and all um, the times in the same unit, it'll work out just fine. Okay, we'll actually see that right after the test with momentum. And there are some times in physics where you can get away with not using MKS, and it's in situations like this where the equation is symmetrical on both sides, so that as long as you've got the same units for R on both sides, then you'll have the same units for R cubed on both sides, and the units will work out. Okay. So I'll say more about that like after the test. Okay, so it saves you a step from converting to MKS units. All right, so then for the Earth's orbit, we're just going to put in the number 1. Okay, so like 1 astronomical unit. So that's 1 cubed. This is going to be 1 cubed divided by, how long does it take the Earth to go around the sun? 365. I mean, I guess we could have used different units there, but since I give you the days, the asteroid's orbit in orbital time in days, then we'll use days over here. So 365 days squared. That's going to equal the orbital radius of the asteroid cubed, okay, divided by the orbital period of the asteroid squared, okay? And the next line I just multiplied 565 squared on both sides, and then I get down to this, okay? Now, you have to take the cubed root of both sides. And to take the cubed root of something, it's like raising it to the exponent 1/3. So if I raise both sides to the 1/3, then this cube will go away. And that's why I just got an R on this side. I guess I also flipped them around. Okay. And on this side, I've got that number 2.39613 to the 1/3 power. All right. And I don't know how your calculator works, but my calculator, that's how I have to do cubed roots. All right, and that gives me this number right here. Okay, now you'll notice that it's bigger than 1, and that's what you expect. If it takes longer to orbit the sun, then you're further away. The further out you are from the sun, the longer it takes to orbit. Okay, so the Earth takes 1 year. Jupiter takes around 12 Earth years to make one complete revolution. I think Saturn takes 20. I don't remember them all. Mercury takes only 88 days. I mean, it takes us 365, but Mercury's closer, so 88 days. So the closer you are, the faster you are. But it kind of makes intuitive sense, okay? So, this is taking longer, and so it's going to be further out, and so R is bigger than 1, okay? How much bigger than 1 is it? Well, I mean, it's 1.33815, and this is 1. So it's bigger by 0.338, and that means that the orbit is 33.8% bigger. Okay, so if the Earth's orbit is this big, the orbit of this asteroid is going to be about 1/3 or 33% bigger. Okay, so there you go. There's an example of using Kepler's third law to relate orbital radii to orbital periods for different planets. Okay, let's move on to energy. Well, actually, let me see if there's any questions in the chat here. No, no questions. So let me move on. Let's do this energy problem right here. Okay, and what does it say? I have a spring. Whoops. Let me put it down here so that my image isn't cutting it off. Okay, so I have a spring with K equals 1,000 newtons per meter. Okay, that's the spring constant, and it's compressed by 10 centimeters, and it's going to fire a 55-gram mass straight up into the air. Okay, and I want to know, how high does the mass go before it stops? In other words, its maximum height. And how fast is it moving when it's 3 meters above its original height? Okay, so it's actually going to go up to about 9 meters, and so it'll pass the 3 meter mark, and I want to know when it passes the 3 meter mark, how fast is it going? Okay, just to show you a picture of what this looks like. Here's a picture. Okay, and so here's the spring here, and this in red here, I'm trying to indicate that I've actually compressed the spring by 10 centimeters. Okay, and I've got this square box here. That's my 55-gram mass, and it's sitting on top of the spring, and it's kind of, the spring is loaded, compressed, and then I release the spring, and it's going to pop up into the air, and when it gets to its maximum height, of course, it stops. Okay, and it's also going to pass the 3 meter mark. Okay, now a few other things to notice here before I actually solve it. We can take h equals 0 right there. Okay, that's after the spring has been compressed. We can say that's h equals 0 for calculating um, gravitational potential energy. Okay, and at that point the velocity is 0. Okay, because like I've compressed the spring and I'm kind of holding it there. So is the box moving? No, I'm holding it there. Okay, so there's no velocity, and I'm also taking that as h equals 0. Okay, at this point right here, all the energy is going to be in the spring. Okay, now it's going to pop up, and then when it gets to its maximum height here, well then the spring has released all its energy, so there's no energy in the spring. It comes to a halt again, the velocity is 0, so there's no kinetic energy, and all the energy is going to be into gravitational potential energy. Okay, when it's here at the 3 meter mark, okay, it's got a velocity, and it's at 3 meters, so it has a kinetic energy and has a gravitational potential energy, but the spring has sprung. The spring is completely uncompressed, because it's at 3 meters and the spring was only compressed 10 centimeters, and so there's no energy in the spring, but there's energy in both gravitational potential and in uh, uh, kinetic energy. Okay, so keep that in mind, and we'll solve the questions now. All right, so the first question was, how high does it go? How high does the spring, the mass go before it comes back down? Well, you know that you're going to have to use energy, so let's calculate the energy, the total energy. And the total energy, uh, you know, because you know it when the spring is compressed. Okay, you can start with this equation right here, which will work at every point in the dynamics. Okay, so what does this equation say? So I use the square brackets to indicate kinetic energy. So there's kinetic energy, and there's only one term to the kinetic energy. There's only one way to calculate kinetic energy. That's 1/2 mv squared. Okay, so that's kinetic energy, and then this square bracket here, that's your potential energy, and there's two contributions to potential energy: gravity and the spring. Okay, however, initially, when the spring is loaded down here, let me show you back on the diagram. Initially, right here, okay, let me do it in purple, like right there. Okay, when you're right there, there's no velocity and no height. Okay, and so initially the velocity is 0 and the height is 0. Well, if the velocity is 0, then the kinetic energy is 0. There it is. And if the height is 0, then the gravitational potential energy is 0. There it is. And all the energy is in there. Okay, so 1/2 K is 1,000 newtons per meter right there. Okay, because I tell you what it is. All right, and I've compressed the spring by 10 centimeters, converting it to MKS. That's 0.1 meters. There that is. Okay, and that works out to 5 joules. Okay, so we didn't answer the question yet because I asked how high does it go, but we're going to use conservation of energy. So there it is. It's 5 joules. Now we can use that energy here. So we know it's 5 joules down here, and that means that the energy up here is also 5 joules, the total energy. All right, so do it again. Do the same calculation again, like that. Okay, and when you do, though, now you're at the top. So at the top, the velocity is 0 again, and it started at 0, then it moved up, and then when it got to its maximum height, it stopped again, so it's 0 up there. The spring has uncompressed, so x is equal to 0, because x is the measure of the spring's compression. All of the energy is where? It's in mgh. Okay, so let's go ahead and substitute in what we have. Do we have E? Yeah, that's kind of the point. The whole point of doing this was to get that 5 joules. Okay, so now we know the energy up there is 5 joules. Okay, the kinetic energy up there is 0. Okay, mgh, for m we have 55 grams, but we got to put it in kilograms. Okay, so here I had 55 grams. To convert that to kilograms, divide by 1,000, so it's 0.055. So there's the mass in kilograms. G is 9.8, rounding it off to 10 as we always do. And then H, that's what we're trying to solve. How high does it go? Okay. And then there is the potential energy due to the spring, but the spring is uncompressed at this point, and so that's 0. Okay, and so that just reduces this, and that tells us that it gets to a maximum height of 9.09 meters. Okay, so there you go. There's your maximum height, and it answers this question right here. How high does the mass go before it starts coming back down? All right, the last question, or second question, I guess, is how fast is the mass moving when it passes the 3-meter mark? Okay, well, it will definitely pass the 3-meter mark because it's going to go up to 9 meters. Let's go to the diagram again. And so now we're looking right here. Okay, we're looking right there. All right. And what can we say? Well, x is 0 there. I guess I didn't write it in here in blue, but x is 0 because it was only, the spring was only compressed 10 centimeters. So when it sprung, it went back to 0. So you're at 3 meters, which is bigger than 10 centimeters. So the spring is out of the picture. Okay. There is a velocity because it's still moving up. It hasn't reached the 9-meter mark. Okay, and the height is 3 meters. Okay, and so let's make use of that and calculate how fast it's moving at that point. All right, so here we go. All right, start from the same equation again. All right, I mean the form of the equation is the same, just the values of the numbers are going to be different at different points. Okay, so yeah, we still have kinetic energy and potential energy and 2 contributions to the potential energy, but now when h is equal to 1 meter, the velocity is whatever it is, I don't know. Okay, and x is equal to 0. All right, and so let's plug in. Do we know the total energy? Yeah, it's 5 joules everywhere. Okay, 1/2 mv squared. Well, we have a half. The mass 55 grams. That's 0.055 kilograms. V squared we don't know, but that's what we're trying to calculate. Okay. mgh, m is 0.055 grams. G 10. H is 3. Okay, 3 meters high. Plus the potential energy due to the spring, but the spring doesn't have any potential energy left. Okay, so that reduces to this. All right, and then just subtract 1.65 from both sides there. Divide by that number there, and then take the square root, and I found that the velocity is 11 meters per second. Okay, so when the mass passes on the way up, when it passes the 3-meter mark, it's going to be traveling at 11 meters per second. So it starts off at 0 when it's on the spring, and then the spring shoots up, and then it's got some velocity, it gets accelerated, and then as it goes up, it's actually going to slow down because the velocity, the kinetic energy is going to become potential. When it gets back up to the very top, it's going to stop again. Okay, so it went from all potential energy in the spring to a mix of gravitational potential energy and kinetic energy, and then at the very top it's all gravitational potential energy. Okay, and that's how this problem gets solved. So I thought it was a little bit of a variation on, I usually do the roller coasters, with cars going downhill and uphill, and then there are springs involved and so on, and those are good problems too, but I just thought I'd show you that this could be applied to this other situation here, which is a little bit different than a roller coaster. Okay, so there we go. That's our energy problem. Let me see if there's any questions in the chat here. All right, well, we're going to do an oscillator problem, and then we're done. Okay, it'll be kind of a short class, but before we do, I did invite Physics 111 to just whoops, I lost the it happens. There we go. I did invite Physics 111 to watch the energy problems because I didn't get a chance to do it for them. But what I have highlighted here is not for Physics 111. It's just I'm going to do just a very quick review of some of the calculus that related an oscillator to a spring. So if you're a physics 111 student, just don't look, okay? When we get to question 7, then you can start paying attention again, okay? So I just don't want to cause confusion because that's not part of your course at all right? So for physics 101, we're talking about springs. I've got this potential energy for a spring, and we were talking about springs, and then suddenly I bring in oscillators, and you go, well, what's the relationship between springs and oscillators? Well, intuitively, I think you realize that if you put a mass on a spring and you know, compress the spring or stretch the spring and you let it go, it's going to oscillate back and forth. Well, that's intuitive, or qualitatively, but we could actually prove that springs cause simple harmonic oscillation, okay? And simple harmonic oscillation I introduced earlier in the course because I gave you this, okay, when we did the kinematics of oscillation, okay? Basically, oscillators, they just do sinusoidal motion back and forth, okay? Either sine or cosine. I chose the cosine. It doesn't really matter. I don't even know why I chose cosine instead of sine, but I did, okay? And there it is. So what's the relationship? How can you go from a spring and prove that a spring pushing a mass back and forth will actually do simple harmonic motion? And this was the derivation that I showed you. You start from 3 things. First, you start from the fact that a spring, when you compress it or you stretch it, the amount of stretch or compression that you get is proportional to the amount of force that you apply. So, if you apply like 1 Newton, it stretches this much. You apply 2 Newtons, it stretches twice as much. You apply 3 Newtons, it stretches 3 times as much. 4 Newtons, 4 times as much. In other words, the amount of stretch that you get is proportional to the force you apply, and vice versa. And that's this equation right here, okay? And this is also known as Hooke's law. I think next semester you'll do a lab on Hooke's law, okay? And F is equal to minus kx. The minus is just because if you push one way, the compression is the other way. Okay, if you push this way, I'm pushing that way. Well, then, it wants to restore in the opposite direction. Okay, so that's what that negative sign is. All right, and K is a measure of the stiffness of the spring. Okay, and so the stiffer, the harder it is to compress, right? The less compression, the less X you're going to get for the same amount of force. All right. So K is this spring constant. All right. That means that no matter what oscillator you have, whether it's the tiny little cilias in your ear or a skyscraper, anything that has some kind of rigidity has a K associated with it. You don't have to have a physical spring in there. Just like anything that's rigid has a K associated with it. Okay, great. So you have that equation. You also have Newton's second law, which is this equation. Okay. And this is the part that makes it non-physics 111 friendly. There's a relationship between the acceleration and the position, and it's the second derivative. The acceleration is the second derivative, okay? And so now, if we plug this into Newton's second law, and we plug this in for the acceleration, Newton's second law turns into this. I mean, it doesn't look like Newton's second law there, but it is. That's your F, right, from this, right? There's your F, is equal to M, and there's your A. Okay, and now let's divide both sides by negative K squared. I guess I could even put another line in here, because you might wonder, geez, how did you get that? So over here I've got like minus M divided by K, like that. Oh, actually, I want to do it the other way around. I'm glad I did that, actually, because I noticed I made a mistake. This should actually be like this. Negative K divided by M, okay, multiplied by X. All right, I made a mistake there. Okay, and that means I should get rid of that and then move this to the other side there like that. Okay, good. Okay, I lost an X there. Okay, so what did I do here? Well, I divided both sides by M. Okay, so you can see here I had K and now I have K over M. So I have the second derivative of X is equal to minus K over M times X. And I'm going to rewrite that K over M. I'm going to call that omega squared. And that means that I get my first formula that's useful, which is omega is equal to the square root of K over M. Okay? And you say, well, what the heck do you do with this? Well, it turns out that if you take this and you differentiate it twice, right here, so that says take X and differentiate it twice, you get that. Okay, so what does this prove? This proves that if you have if you start off with a spring, you get sinusoidal motion. Okay, and the way it proves it is that, there it is. There's the spring causing, acceleration, and you say, all right, well, what x could I use in there? And you could try a lot of different x's. You could try like polynomials and things like that. The only thing that's going to work to solve this, the only thing that says, look, if I differentiate it twice, I get the same thing back again, is a sine or a cosine, okay? And there it is. And the other thing is when you look at this and you say, what's the period of that? It's related to omega by that. And there's the second equation that's useful, okay? So this equation is useful for the angular frequency, and that equation is useful for the period. All right. By the way, this is going to become much more important next semester, so don't mind this over the break, okay? Because when we do, whoops, I lost it again. When we do waves, it'll come up again. All right. So Physics 111, you can start listening again, okay? So here we go. Here's our problem that we're going to solve, and then we're done, okay? So we make an oscillator with a mass of 3.5 kilograms and a spring constant of 15 newtons per meter. And so, attach this spring, attach this mass to the spring. And then, it wants to sit at equilibrium. My finger here is equilibrium. Mass wants to sit at equilibrium. I'm going to stretch it out 55 centimeters or 0.55 meters, okay? So I displace the mass a distance of 0.55 meters, and then I release it from rest, okay? So I pull it out here, and I don't push it. I just, it's there at 55 centimeters, and I just let go, and it'll start to swing back and forth, okay? So that's what we have. All right. So the first question is, what's the period of the motion? In other words, how long does it take to go back and forth once? And you take a look at this, and you go, geez, how would I answer that? It doesn't seem like I'm giving you enough stuff. Well, you don't answer it directly. There's the equation for the period. Whoops, it's being cut off, okay? Well, let me just put it down here, okay? So there's the equation for the period, but then you say, oh, well, I do have K and M, so I can get omega, okay? So that's this equation right here, okay? And, all right, and so now it's just a matter of plugging in numbers. Let me just cut and paste that. All right, so omega right here is equal to the square root of K over M. All right, and for K I put in 15, and for M I put in 3.5, and that gives me a frequency of 2.0702, and the units are hertz, okay? So then I don't want I didn't ask for the angular frequency, although I'll tell you right now, as soon as you've got a problem with simple harmonic, oscillators, you're going to be working with omega one way or another. It's hard to avoid it. Okay, so then the period here, that's going to equal 2 pi. So there's 2 times 3.14 divided by the frequency, and that gives a period of 3.03352 seconds. On a test, I would round that off to 3 significant figures. That's what we've been doing throughout the course. So t is going to be equal to 3.03 seconds. Okay, so I pull it out here, and this thing's going to go back and forth, and if I start it at this point, I start my stopwatch and I say, how long does it take to go there and back? A full cycle, 3 seconds, just a tiny bit over 3 seconds. Okay, next one, what's the amplitude of the motion? Okay, so I wouldn't say it's a trick question, but there's no calculation that you need. Basically, the amplitude is just the furthest displacement from equilibrium, okay? And at that point, the velocity is 0. So, if equilibrium's here, if equilibrium's there, and I pull it out here, and I let go, it's going to go back and forth. What's the furthest it's going to get from equilibrium? Well, that's where v is equal to 0, and that's at the end point at the 55 centimeters, okay? So, there's really nothing to calculate. You say, well, how would I know that? Remember, wherever v is equal to 0, wherever the velocity is 0, that's the amplitude. Okay, that's going to be your maximum displacement. Think about it. Once it stops, it can't go further out. Okay, so wherever it stops, wherever its velocity is 0, that's its maximum displacement. Well, we released it from rest, so that's 0 velocity, and that means that's the maximum displacement, 0.55 centimeters. Okay, all right, so 0.55 meters, okay, or 55 centimeters. Okay, that answers that question. What's the maximum velocity? So there's actually 2 ways to do this. One is using the kinematic equation that I gave you last uh, uh, the first third of the course, okay? But let's do it using energy because that generalizes a little bit more, okay? So we'll do it both ways to show you that you can do it both ways, all right? And so first you're going to get the, uh, I'll cut and paste the whole solution here. First, let's get the total energy. And so there's, oh, sorry, I went highlighted too much. There's the equation for the total energy right there. There's the kinetic energy there, and there's the potential energy there. And the potential energy is only the potential energy due to the spring. Okay, there's no gravity in this. There's no MGH. Okay. So did I give you enough information? Well, yeah. V is equal to 0 when x is equal to a. Okay, so just remember a is the amplitude. We could have called it x max, except that every other textbook in the world calls it a. All other physics courses call it a. So for conventional reasons, we have to call it a. But you can think of it as x max. It's your maximum value of x. Okay, and we just argued that that's going to be 0.55 meters. Okay, but at that point the velocity is 0. So when you plug into this, the kinetic energy is 0 here, and that one is equal to that 0.5. K was 15, and A was 0.55 squared, and that gives you this energy there, which rounds off to 2.27 joules. Okay, now that doesn't answer the question, that just tells you the total energy, but now we can use that to calculate the maximum velocity. Okay, so at the endpoints, all the energy is potential because there's no velocity out here, so all the energy is potential, and this thing oscillates back and forth, back and forth. The endpoint, it's all potential. By the time it gets to the middle, to equilibrium, x is equal to 0, and when x is equal to 0, all the energy is kinetic. Okay, because x is equal to 0, so it's maximum velocity, all the energy is kinetic. And then back out here, it's all potential. So it goes all potential, all kinetic, all potential, all kinetic, all potential, like that. And then if it's like somewhere in between, it's not at the end point and it's not at equilibrium, then it's a mix, a little bit of kinetic and a little bit of potential. Okay, and so I have that equation right there, all right, which is kinetic plus potential. But we're at equilibrium, so at equilibrium, V is equal to V max, that's your maximum velocity, and x is equal to 0. So this time, your kinetic energy doesn't disappear, all right, but your potential energy does. Okay, and the energy here, well, we calculated that above, okay, and that's equal to this, all right, and that allows us to solve for V max, and we get that V max is equal to 1.44 meters per second, all right? So that's one way to answer it. In my previous class, someone said, well, I remember this equation here that you gave us way back when. In fact, I didn't give it to you. I actually derived it. V max is equal to omega A. It's totally correct. It's, it's not different. Okay, it'll still work. And so I showed them that it would work. I just plugged in for omega here, and I plugged in for A, and sure enough, I get the exact same number. Okay, now that was obtained using kinematics, and this one was obtained using energy. But obviously, the two can't be in contradiction to one another. Now, the reason I did it this way is because this approach generalizes. Okay, this equation here will only work to equate the maximum x, in other words a, and v max. So, okay, but in my next question you would see that there's no equation that you can possibly use there except for a conservation of energy. So if you take a look here, all right, I asked the question, how fast is it going when it's 0.25 meters from equilibrium? Okay, so its maximum is going to be 0.55, and now it's at 0.25. It's closer to equilibrium, so it has some velocity, and we wonder how much velocity does it have. Well, you certainly can't use this equation because it won't work there, but this one will. Okay, that one will. Only now, it's not that v is equal to v max. V is equal to question mark. We don't know. That's what I'm asking. How fast is it going? And x is equal to 0. X is equal to 0.25 meters, like that. Okay? And, the energy is still the same as above. So we can plug in that energy, and we'll know all the other quantities in here except for v, and we can solve for that. All right? So let me cut and paste that solution. Okay, So what did I do? Here, this number right here, that's your E, okay, is equal to 1/2. M was 3.5 kilograms, okay. V we don't know, but that's what I'm asking for, how fast, okay. 1/2, K was 15, and X, we're not at maximum displacement now, we're at 0.25 meters, so 0.25 squared, and just working that through, that comes out to this number, which is 1.01 meters per second. Okay, so that's how fast it would be going. Now, um, you could say, does that number make sense? Well, compared to Vmax, the maximum velocity is going to be 1.44, and it's less than Vmax, so yeah, it makes sense. Okay, so think about it this way. My extended finger here is equilibrium. When you're out here at the 55 centimeter, 0.55 meters, it stopped. Velocity is 0. But then it starts to move towards the middle. Okay, and as it moves towards the middle, it goes faster, 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 faster. Right at the middle, it's reached 1.44 meters per second. Okay, well, if you're out here, you're not at 0. So not all the way out at the end, but somewhere in between. You're not at 0. You're not at the 1.44. You're a little bit less. You're between 0 and 1.44, and 1.01. It's within the right limits. Okay, so you should check your numbers, or think about the answer that you got, make sure that it makes sense. If you had done this problem and for some reason you came up with v equals 3, you should say, wait a sec, how can I get a velocity of 3 if my maximum is 1.14? And so, yeah, you would have noticed that there's something wrong. Okay, so there you go. There's a quick example of harmonic oscillator problem. Okay, so with Monday's class and this one, I've reviewed everything that's on the test. Okay, so if there are no questions, we're done. Let me take a look here in the live stream. Okay, so we've had 2 dedicated viewers throughout. That's all right. I mean, 2 viewers is better than 0, I guess. All right, if there are no questions, let me just type it in the chat here. If there are no questions, then we're done. I'll wait just a second here to see if anyone has any questions. All right, doesn't look like it. Let me just say goodbye. And, if you have any questions, then catch me during my